Well, hello friends. Today we are going to start on something new, something a little bit ambitious. So one thing I really miss from using Linux is valgrind, because I love using valgrind to find memory problems and just hard to catch bugs in my code. And on Serenity we have nothing like it. So I figured we would build our own thing that does the same job. And the way valgrind works, to my understanding, is that it's basically a user space CPU emulator that just sort of runs the code in a virtualized environment where it's able to intercept memory accesses, and then it will know at like an instruction level when you're doing some kind of memory access, and then it's able to instrument that and say like, oh hey, this read that you're doing here is actually outside the bounds of what you previously mallocked or whatever. So I think that's a fantastic tool, and we don't really have anything needed to support that, so I figured we would build it. Now, I guess we're going to start with kind of a simplistic approach. So my idea is that we'll build a user space CPU emulator, and basically we'll make like a fake system that you can run a program in. And what we'll do is we'll like load that binary, put it into fake memory, and then we'll like step through the CPU instructions one by one and do whatever we want to the memory accesses, like instrument them somehow, right? But it's going to take a fair amount of work to get to the point where we can actually use it to analyze and catch bugs. First thing we have to do is just get a user space CPU emulator up and going. So that's what we're going to do today. So I have done a little bit of preparation for this video because I didn't want to do this super boring task. So what I've done is I've added this thing called an interpreter to libx86, and it's just a class that has a whole bunch of pure virtual functions, one for every x86 instruction, essentially, for like all the variants of them. So these are all the instructions that we had in our disassembler. So I just took this from sort of the disassembler data. So if we go and look in the instruction class, which is, this is our disassembler stuff, or we use it for the disassembler right now, it has builds this big table of these. And the thing that's new is that for every instruction that we know how to disassemble, we also now have a pointer to a member of the interpreter class. And then the idea here is that you'll be able to instantiate your own interpreter subclass and implement all of these things, and then create like a CPU execution loop or whatever that that can dispatch the correct instruction callback. So anyways, that's all that I've prepared. I just didn't want to do this big text editing task. So so let's just get started on some kind of emulator. So I guess we will put this in DevTools. And what do we call this? User space interpreter? User space emulator, maybe? User space emulator. That's not so bad. Okay, so then let's just copy in some kind of CMake list prepared. I don't know, I don't want to write my own CMake list. I don't know why that seems so important right now. It's not like writing this is very hard. Okay, so user space emulator will probably need like libcore, and I don't know. Probably we're not going to go so crazy with it. But yeah, so this is what we'll start with, and then I guess we should have like a target program that we want to be able to run. So let's also make like a very simple CPP program called simple CPP. And what we'll do in there is that maybe we'll do a syscall actually. So we'll do like something like this. I don't know, we just need a test program to get started, right? So we'll do syscall get UID, and then we can exit with the UID as the exit code of the program. Does that build? Yes, it does. Okay, so let's just take a look at what that program looks like assembly-wise. So that goes in userland, simple. Cool. And of course, we'll just make the emulator jump straight to main for now, even though technically we're supposed to jump to _start, which is where programs actually start. But we'll just skip ahead to main. So what this will do is that it will run some instructions to set up a syscall, and then make a syscall, and then set up another syscall, make that syscall. So this is the get UID, and then we have exit, and then we have return code here. Of course, the exit thing will actually kill the process. And my thinking is that when we get these software interrupts, so basically system calls, then we won't call the kernel directly, right? But we'll instead have like a syscall interpreter layer in our user space emulator that will look at like, okay, so what syscall is the emulated application trying to make, and then we'll have to react to that in there. But yeah, so I think we should be able to make this program run today if we start now. That would be kind of cool. So it'll be a program that exits, and the exit code will be the user ID of the user who ran the thing. Okay, so we'll just start with a simple main file, and I guess I should user space emulator, and maybe I should make an alias for this right away, because we already have all these aliases. These used to be symlinks, but now we have alias support in the shell. Thanks Ali for adding that, by the way. So now I can just add it here and say like UE, which is the user space emulator, and then that's available. Okay, so that's enough chatter. What do we do here? User space. Oh wait, why is it not indexing? Oh, did I not create the main file maybe? Okay, let's try that again. There we go. Okay. So, first thing is we'll need that interpreter. I guess we're gonna put that in a separate file immediately. This will be our we'll call it like the CPU we'll call it the CPU. Maybe the soft CPU even. No, I meant to delete the other one. File management problems. Okay, soft CPU, that's a cool name for a class. Let's call it that. Soft CPU. Okay, so this will include libx86 interpreter. Okay, and then we can close that. And this is going to be a soft CPU in the user space emulator namespace. Okay. And all of these instructions, they're going to be x86 instructions. So I guess we can do this. Just do a little bit of search and replace here. Okay. And none of these should be pure virtual anymore. So we'll do like replace that by override, I guess. Boom. And then we'll say that this is a final public x86 interpreter. Okay, and then we just need to implement all of these functions. That's going to be super fast. obviously it's going to take time to implement everything, but I think we can just go like we'll just go like one thing at a time and do the thing that we need. So like we'll do one instruction at a time, right? So the first thing we'll need is like this mov instruction right here, and so on, and we'll do it incrementally. Because if you try to do this kind of task and you just like start at the top, like, okay, let's do this instruction, you'll be bored to death before you get anywhere. So this is just too many instructions. So let's see. Okay, so we need the CPP file for this, soft CPU, CPP, soft CPU, and all of these guys, and then we'll remove the virtual. Click. Oh no, that's not what I meant to do. Dang it. Virtual will go away. Override, go away. And then maybe the, wait, can we do regex here, please? So, void, this will become void soft CPU : right? Okay, and then we just need to do the, I guess I don't need regex actually. Wait, can I do multi-line here? Advanced. I don't know how to do multi-line. Maybe that's what some of these things are. I don't know. Multi-line, in search and replace, multi-line is always this thing that's kind of missing, I feel like, in every text editor. There's probably a way to do it, I just don't know how. And probably I'm talking out of my ass, and every text editor ever can do it, I just don't know how. But at least they're hiding the feature, I can say that much. So what we want to do is we just want to do a, maybe we want to do like a to-do like that. Yeah, I think that'll be good, because then we can, to-do is essentially like assert not reached. So it's just a more expressive variant of that. So we have all of those, and then we can just implement these as we go. And if we try to execute one that we haven't implemented, it will hit the to-do macro and crash. All right, so let's see. And then, wait, let me not forget putting a copyright header here, because if I forget, then the build bot will be sad. So, likewise here. Okay, so this is our main function. And, oh, and we're going to need libelf for this, by the way, so that we can like interpret elf binaries. So let's see, libelf, definitely useful. And does this thing actually build? Oh wait, that's not how you do that. Wait. Oh, maybe libelf is part of libc or something? I don't remember how that's built actually. I think it's part of libc. Let me see. Elf. Yeah. Okay. So the elf library is built into the C library. So if you're linking against libc, then you have libelf. That's convenient in this case. Okay. Oopsie doopsie. Go away, copyright header. libcore args parser. Okay. I'm just trying to be a good boy now and adding the args parser early. It's not that I want to use it for anything right now. I'm just adding it anyway. Maybe I should use it for something though. Maybe I should use it for the executable path. Yeah, maybe that's better. Okay, so args parser, add positional argument, executable path. Executable path. Required yes. Okay. And then, what do we do? This is very uncharted territory. Like, I haven't done anything like this. I've built emulators before, and I've built an x86 emulator before. So obviously I have a lot of experience from that I can draw on here, but I've never made any kind of user space emulation. So this is a little bit strange. We'll see. I think it could turn into something really interesting. So we need the soft CPU. Okay. And then I guess we'll just make one. Call it the CPU. And so this thing has all the instructions, right? And then we need some more stuff. So we need like libelf, what's that thing called? Loader. And we need x86 instruction. And then we need to, maybe the first thing we should do, let's look at the code that we had. In this simple program. So this is pretty simple actually. Like, it doesn't have any memory accesses or anything like that. So we can kind of postpone implementing a memory management unit, and we can just focus on interpreting instructions right now. So I think we'll just load up the executable that you're specifying. So we'll do elf loader create. Oh, we have to specify, right. So we have to actually map it somehow. But we have mapped file, which we can use for this. So mapped file is executable path. If mapped file, if it's not valid, then that is a bummer. And I should get better about using these expressive error helpers. What are they? Warn, that's the name. Do we have like fatal or something? No, I don't remember what I add. But I remember that we had this. So unable to open, unable to map. Yeah. Okay. And then we will mapped file data, mapped file size. And I guess we have to cast here from void star or whatever that thing is. Okay. If elf, oh wait, does this always succeed? I guess it probably does, yes. But then how do we know if it was valid? Let's see, what does this thing do? It's been so long since I've looked at this. So I think we just instantiate the loader, and that should be enough. Hopefully. Okay. And then we should find the main function. So main symbol is elf image symbol for, no, wait, what is this thing called? Find symbol, find demangled function, right, main. Okay, so we'll go looking for main, and if main symbol, is that a thing? I don't remember how this thing works. Oh, it returns an optional. Okay, that's easy. So if we don't find it, then we can also fail. So warn, could not find main symbol in executable. Okay. And then otherwise we have the main symbol and the main symbol value main code is the raw data. I think that will be our pointer to the code, yes. Or we can do like this and we have a string view, which is bounded. Okay, so then let's just try to disassemble this, because that should be pretty straightforward. So forever, we'll wait with the CPU stuff for now. So forever, x86 instruction stream. Oh, nice. Okay, stream. How do we create a stream? A simple instruction stream created over a data and size. That's perfect. So a simple instruction stream created over main code length. It's a bit weird that this thing gives us a string view, but I mean it's fine. It's just it's a little unusual because it's not a string technically, right? It's not a string of characters anyway, or it's not null terminated. Anyway, it's just a pointer and a size. That's what matters here. But this is not good because we need a const u8 star, but we can just cast. Cool. And then stream. Wait, how do we get an instruction? Instruction is x86 instruction from stream. Stream. And then I think we will just assume 32-bit mode for now, and then this will become a state of the CPU because x86 CPUs they have like it's kind of complicated, but they have like you can have 16-bit or 32-bit operand size and 16-bit and 32-bit address size, and then you can mix and match. So even though you're running in 32-bit mode, you can like temporarily switch one instruction into 16-bit addressing mode and things like that. And we have to keep track of that. But for now, we'll just assume that everything is 32-bit. This kind of stuff will have to go in the soft CPU eventually. So we'll fetch an instruction, and then maybe we can just toString it. And the origin is our address that we found the instruction at. So we need to keep track of our offset here. So main code, main symbol dot value. That's the memory address, the virtual memory address of the symbol. And then ignoring the rest, plus offset, right? Plus equals instruction length. Okay, I think that's our loop, and then we'll just log the instruction. Instruction. Something like that. And then I guess when we get to a ret instruction, we should exit. So we can do something here like if instruction mnemonic is ret, then break. Something like that. I need to link against more things, probably. I forgot about libx86, which seems like the most important library in retrospect. Okay, so UE is the user space emulator, and we'll run it on bin simple. And it correctly interpreted each instruction. I mean, it disassembled them, right? So we're stepping through the main function and seeing each instruction here that we need to execute. That's super good. And then the next step, by the way, we should probably hack this a little bit right now, just to make this a little bit easier to deal with. La 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 la. Proper. Yeah, we'll do that. And fix me. Enable this. Yeah. So we shouldn't forget about that. So what do we want to do now? We want to actually invoke the handler on the soft CPU for each of these things. So what we'll do then is I guess we'll do it after we print the instruction. So CPU dot, oh man, I never remember how to invoke member function pointer. Is it like this? Oh wait, maybe we don't expose that in some way. I need to actually expose it, because we have interpreter. This is the type of callback thingy that we have. So we just need to actually hand one of those out from the instruction class. Forgot about that part. So we'll just do here. Class interpreter. And we can do that. And then instruction handler. Yeah, that'll be good. Maybe it can even be const. And then we just need to expose that. So instruction handler returns descriptor handler. Okay. And then ensign handler indirection requires, oh man, I don't remember how to do this. It requires a, oh, it has an argument, right? So oh, I gotta look this up. I so rarely use this feature of C++. Pointer to member function C++. Let's Google it on Bing. That's the way it is. Okay, so there we go. Okay, that's like, it's, I don't use it often enough to actually remember it, so that's what you get. I guess we can put some hack here, just void these out, just to make it build. And oh, we need a vtable for the soft CPU. We forgot about adding that here. Okay. So I'm hoping now that we'll crash in one of those to-do things. So we're assertion failed is one of our to-do macros in soft CPU line 257. 257, that's right here. So it's a MOV and 32-bit immediate into a 32-bit register. Very good. So that'll be our first instruction, right? That was the instruction that was printed here. So moving a 32-bit immediate value, 7, into the 32-bit register EAX. So then we just have to do that. This will be fun. So here, let's see. So I guess we need to include libx86 instruction. And then right here, we know the register index. So the register index is it's one of these guys. So this tells us which register to move into, and really the soft CPU is gonna need like some registers that it can store stuff in. So soft CPU, maybe we will just add some registers at the bottom. That would be the easiest. Private. So let's see, U32. EEX, EFX. No, I can't do that. Have to have the real names. Okay, so these are the 32-bit general purpose registers of the x86. It's probably, we'll end up defining them in a more sophisticated way later, but right now this is straightforward enough for me. Maybe we'll call them M like this, just to be consistent with every other class ever in Serenity. Okay, so then based on the register index, so we'll write this out in a very obnoxious way right now, but later we should make a lookup table probably. So this would be like register EAX. What's that, x86 register EAX? Yes, MEAX is instruction in 32-bit immediate. Break. Okay. Okay, this is going to get super obnoxious, so I'm just gonna make a lookup table right away. So we'll have something like reg32 table, and we'll also add a constructor for this class, so soft CPU. And then that constructor will be nice enough to set up a lookup table here, because otherwise this is going to be very tedious and very verbose. So yeah, something like this, right? Okay, and then we should be able to use that instead. So we'll just say M reg32 table, instruction register index is in M32. Okay, that is basically the implementation of that function. Now, we should probably have a way to dump CPU state so that we can dump after every instruction. That would make it a lot more interesting to look at execution. So here, I think after every instruction, we'll just dump the CPU state. Like that. Okay, and then here we will just say like out, or probably we're going to want this to look in a very specific way, so we can do something like this. Okay, we'll start like this. Actually, I don't know why I don't just put everything on one line right now. We can fit more registers on the same line. But should we? Maybe 4 per line is fine. Okay, I'm really stressing the important stuff right now. Base pointer, stack pointer, source index, and destination index. Alright. And then load the x86. Oh no, we need stdio for this. Using printf. So I'm hoping that we'll be able to execute this instruction, print out the CPU dump, and then crash in the next one instead. And look at that. We're executing one instruction, and then the state of the CPU is that we now have 7 in our pretend EAX register. Pretty cool. Okay, so what's the next step? I guess just doing the next thing. So now we're crashing on 197. So that's a software interrupt with an 8-bit immediate. So this is our system call basically. So here, let's see. So for now we can just assert that the immediate is x82 because that's the software interrupt number for Serenity system calls. So if you try to make any other software interrupt, let's just crash you for now because we have to emulate the behavior of these things. And one thing that's really nice about user space emulation is that you can ignore everything about like operating system concepts in the CPU, or not everything, but a lot of it, right? And you can focus only on the stuff that's relevant when you're running in Ring 3 or the user space privilege level, which makes this a lot simpler than it would be if we had to support like the full range of CPU capabilities. So let's see. What do we do? I guess syscall, and we could even print out the name of the syscall if we get the syscall header. Kernel appy syscall. Okay, so we'll print out the name of the syscall, maybe like, I don't know, we'll print out the number and then the name. This, or maybe the name and the number like this. That would be cool too. So let's see. We syscall to string syscall function m8. Okay. And that's our implementation. So let's see what it says about that. So the first syscall we were making was getUID. So we should print out like syscall getUID and then whatever number. Or actually, this is going to print out 82, which is not the thing that we want. But let's just see that it gets that at least. Shabuf set volatile. Right, so we're using the wrong number. We need to, the system call ABI that we have, it passes the syscall function number in the EAX register. So here we actually need to look at EAX to know the function. So and like that. EAX, All right. Do we know how many syscalls there are? Enumerate the syscall. Yeah, so we could fail if it will be unknown for anything else. Okay, that's fine. Okay. So let's see. I want to see like get UID. Okay, so it's making a get UID syscall. Very cool. And then my idea here is that we would just provide like fake versions of these syscalls. So that's something that we would put in probably a separate file because this is going to get pretty big. Not make it here. Syscalls. Yeah, we can call it that. Syscalls. Or maybe soft syscalls. Virtual syscalls. Maybe virtual syscalls. That's pretty cool. Okay. So what's this going to look like? I think maybe we'll just let them be free functions for now. I'm not exactly sure. We'll probably end up with some kind of a class thing that holds on to various things later on. But right now we're just kind of freestyling. So we're gonna keep freestyling as we set things up and discover what kind of stuff we need, what kind of objects we need. So I think for now we'll just have like so this is called ABI. The basic ABI is that you pass a bunch of parameters in general purpose registers, and then the return value from the kernel is returned in the EAX register. So our fake virtual syscalls, they really just need to take up to three parameters, and also they need to return a 32-bit value. So essentially, this will be our typical syscall. Get UID. So maybe we'll call it like v syscall, something like that. Looks kind of cool. Maybe even v. Ooh, it's like vert. Ooh, that's really spicy because the way we call the syscalls in the kernel is that they call it sysdollar get UID. It's kind of the naming convention that we use a little bit just for fun, but also to make them look really special. And here we can have like our own little special name for them. So vert get UID can be the name for it. You gotta have fun with programming. So that would be that one, and then we'll also add exit because that's another one that's coming. And exit takes a wait, where is sys exit? Takes an int, the exit status or exit code. So actually it doesn't return anything, but in our case, let's just make all of these things return something because it just makes it easier. So let's see. This thing, actually, no, let's be smart here. Let's not return something if we don't need to. So get UID. This thing can simply fetch the current user ID, right? Like it doesn't need to do anything other than that. So we'll just return get UID. We'll ask the kernel for our user ID. No harm in letting, we don't need to intercept here and do something special, so we'll just ask for a user ID. And then the Xcode, what does the man page call that anyway? Status, okay, status, fine. So this is like this system call exits the program normally, right? Like, but we might want to do something interesting in this case. So we probably want to like print some stats or something like that. So I think we probably want these things to be members of something. What do we want these? Maybe we'll put them in like an emulator object. So, my nose is itching again. Freaking allergy season. I feel like it's been allergy season forever. Okay, we'll call it emulator. Yeah, that's probably better than that. And then actually, we'll do a little swap here or a switch. Okay, yeah, that's better. Close, refresh, emulator. Okay, so class emulator. Here we go. This will be better. So these will be our implementations of these things. And then we'll have like an API here, like U32 syscall. And it will receive all the parameter range, because we don't know what syscall is coming in. Like, we have to have a generic interface for it, since all we know is that we have like a function number and 3 32-bit parameters, and they could mean anything, and then the emulator will figure out what it means. Okay. Oh, did I already mess this up? Oh, whatever. Emulator vert get UID. So that one should actually be a UIDT if we're gonna be like that. Sys types. And then we have emulator vert exit status, which here now we'll do something like shutting the whole thing down, which will take some form. Maybe right now we'll just print out like shutting exit status. Shutting down. Okay. And that'll be good. And then we'll set something like shut down true, something like that. And then probably we should have like an emulator loop somewhere. So maybe we'll put that up top. A main loop for this guy, or we'll call it exec. That'll be cool. Maybe he will get the soft CPU passed to him for now. Maybe he should own the soft CPU later, but right now we can just do this. Okay, so then while not shut down, then essentially we want to do this loop right here. We'll pass in the instruction stream as well. So something like that. And then we can move our loop here. like that, and just passing that in here so we don't need to keep track. So it's a little bit of a hack, but emulator exec, CPU, stream, and the base. Okay. Here we go. Too many frickin' function parameters. All right. Maybe we'll make this return something. Yeah, that'll be nice. And then if we do an exit, we can even stash that away. So like exit status is status, and then we'll return exit status. Okay, and we'll store that. It'll just be 0 if you don't exit normally, like if you exit through this path right here. And oh wait, I'm not doing the system calls yet. Soft CPU. So soft CPU needs a way to find the emulator. So let's see. Probably emulator should own it. So we'll do like this. CPU, you can own me. So we'll do that. Okay. And then wait. That's well, actually that's what I wanted to do. Yeah, right. And then emulator gets a CPU member, so like soft CPU. Yes, that will be good. Don't need the forward declaration. Don't need this. But we do need soft CPU. Okay, we are just quickly rearranging everything here. Missing exception specification. What are you on about? That's strange. Okay, blah, blah, blah. Okay, so now the CPU knows us, so he can actually, when we do the interrupt, well, he doesn't know us quite yet, but he will now. So now the soft CPU has a pointer, back pointer to the emulator, and then we will finally be able to say here, emulator, which we need to include. emulator.syscall. EX. Oh man, what's the order? I forget. So the order is A for function and then D, C, B. All right. There we go. Oh, that's a macro. Oh, dang it. Okay. We'll just call it like VV syscall virtual. That's fine. So we can put like this. Cool. And then I think we'll put the printf in here. An emulator. Okay, so then we'll have emulator syscall printf function. Okay. So function, that part is cool. And then this thing actually needs to dispatch the correct function. So if we'll switch on it for now. Then we'll make a table later. Right now we can just switch. So case sc, what's it called? Get UID. Return vert get UID. Oh, right, exit doesn't return anything. Right. That makes sense. So we'll do that and then that. And I guess we'll have to void these other arguments out for now until we get some syscalls that actually have more parameters. All right. Oh yes, now I changed the object model, so we have to go and change some stuff up. And here we can say like warn unimplemented syscall. And this thing here will tell us what the syscall was. So, yeah, let's not worry too much. Let's assert not reached here. To do, maybe even. Okay, now in the main, we can get rid of this thing and just call exec like that. All right, so we did our get UID, and we're doing this syscall presumably, but I feel like we're not seeing the return value in EAX, right? Because we forgot about that part. So we need to actually set the return value. That would happen in I guess in this syscall function here when we do a virtual syscall. Actually, when we call this thing from the soft CPU, we should do meax equal, like that. Because I want to see my user ID in the EAX register. All right, that's more like it. 64, also known as the hexadecimal version of 100. Very cool. In our fake soft CPU, we now have retrieved the correct user ID from the fake kernel syscall. Very cool. So the next step is, I already forgot. Oh, here, 273. So now we have mov rm32 reg32. So let's see. What was the instruction? Is this one right here. So we're moving into EDX from EAX. Okay, so let's see. I haven't implemented. We don't have like a way because RM32. That means that it's a register or memory location. 32-bit register or memory, and then this is a 32-bit register. And I haven't implemented the memory part of this addressing, but in this case, we know that it's a register destination. So can we get to that part somehow? Let's just expose this. Wait, what's wrong with that? Mutable, whatever, that's fine. So assert that it's a register. Okay. And then we should be able to do something like this. Mod rm register index. Oh, we don't expose that? We need to expose that. But that's easy. Memory or register reference. We know that it's a register, so we can just go here like register. Wait, what do we normally do? Register index. Yeah, just a plain unsigned. And just do the same thing here. So write to the register index, and we put the, oh, now we want to fetch from another register. So reg32 table. Like that. So we write into the 32-bit RM here from the 32-bit register in the instruction. That's nice. Okay. Let's see if this works out. This will become trickier once we have to deal with like memory addresses and stuff, but right now we're kind of coasting on only having to deal with registers. So we can see now that it executed all the way until the end when we did an exit 100, which is my user ID. So that's awesome. And can we see it? The program exited with the exit code 100. So it totally works. This thing actually runs the bin simple program and exits correctly. Very, very, very cool. Man, that's so awesome. So we should probably rename this simple into something else. I mean, ultimately we shouldn't need any kind of test programs, but let's see. Let's do a commit, I guess, but I need to tune up the object model a little bit more first, because this part here is kind of gunky. So I want to pass in the, how do I want this to work? You know what, let's just commit. Let's not overthink it. So what are we doing here? Just exposing some more stuff. x86, expose some more internals, more things on x86 instruction. Okay, and userspace emulator. Start building a userspace x86 emulator. This introduces a new x86 CPU emulator for running SerenityOS user space programs in a virtualized interpreter environment. The main goal is to be able to instrument programs, memory accesses, and catch interesting bugs that are very hard to find otherwise. But before we can do fancy things like that, we have to build a competent CPU, competent emulator able to actually run programs. This initial version is able to run a very small program that makes some syscalls, makes some tiny syscalls, but nothing more. Yeah. But this is really, really cool. And now I regret doing this. I wanted to fix that up. There we go. Let's just amend that. Okay. And I guess, like, what would be a more complicated thing to try to run? Because now it will try to run main in anything that we specify. So, like, what's I'm thinking, like, what kind of programs do we have? We can run like bin true. That's a really small one. Because true is like it just returns. Wait, oh no, that's the PID. It returns success, and false returns failure. So, can we run bin true? We can't, because we have to support this instruction. But we can do that. So that's on soft CPU 521. Okay, that's another RM32 reg32, like the one we just did. So it's just a matter of, let's see. So we need to first, wait, how does this work? So this still immediately gets a bit more complicated, because now we have to care about arithmetic flags, but that's okay. So we'll start by just fetching the two values that we're supposed to XOR with each other. So the destination is let's assert that we actually have a register RM reference, but we know that we have because it's EAX. So if this had been a memory destination, then we wouldn't be able to deal with it yet. But right now it's okay. So we have our thing, register index. That's our destination. Maybe we'll even do like this. It's a reference to it. And the source is just going to be a value, so it's the register index of the instruction proper. And then just do that. And technically that would probably make the program run, although we're skipping over the part where we're setting the flags. So let's be good boys and also set the flags. I don't remember exactly how the flags get set from this. Let's look that up. So I know I have the Intel manual somewhere. Let me see if I have it here. Right, okay, so here we go. Had to go and find an Intel manual. So let's go and look up the XOR instruction. That would be somewhere in the instruction set reference. XOR. And what, my friend, do you do to the flags? So this is what the XOR instruction does. The OF and CF flags are cleared. ZF, SF, and PF are set according to the result. AF is undefined. And then we have like these exception behaviors and stuff. We can just ignore those because we're a user space program. So that part is good. So let's see. So essentially we wanted to clear OF and CF. So I think maybe we'll put some helpers like this, maybe set CF, OF. And then we wanted to set ZF and BF according to the result. So ZF is like whether the result is 0, so that's easy to check. And SF, the sign flag, that's whether the result is signed. So in our case, since this is a 32-bit instruction, we just have to look at the top bit of the destination of the result. And the PF, the parity flag, I think we'll just skip over that one right now, maybe, because it's like you have to compute how many ones are set in the, like how many binary ones are set in the result or something like that. But in practice, nobody ever uses this flag for anything since like 1981. So I think we'll just ignore PF for now. We can set something like fix me set PF. But these we'll care about. So let's see. And by the way, obviously we're not building an optimized emulator here in any way. This is like a very, very simplified emulator. We're not trying to do any sneaky techniques like lazy flags or jitting or anything like that. We are just building something that will work, because I'm kind of suspecting that an interpreter, given the fact that we're not emulating the whole system, but rather only the user space code, and we'll be able to, like whenever you make a syscall, we'll take over. Because of that, I think that this will probably run pretty well, even in just interpreted mode. And we can do some stuff later to make even an interpreter quite fast. Like we can look for optimizable little snippets, like memcopy, for example. We can easily have a heuristic that just detects a memcopy and turn that into an actual memcopy in C++ instead. Things like that will probably make this pretty fast. So I'm not going to worry about that right now. But we need our flags here, so I guess right now we'll just do something like, we'll just set them up. Okay. I don't know what order I want, why that matters. Okay, so, and then we'll have some, let's just have some helpers for this. So, set OF. I don't know why. Like I always just like to have helpers for this kind of things, because I feel like it just I don't want to fiddle directly with the members anywhere if I can avoid it. And I actually already feel a bit awkward about fiddling directly with the general purpose registers. But let's not worry about it too much. Maybe we should have get variants as well, so we can have like Yes. Okay, very exciting text editing happening right now. So there's our set of flags. And wait, these were supposed to be get, not set. And I guess we can include these when we dump. So can we fit everything on one line? That would be kind of cool. We can do something more like this. Make it a little bit tighter. Because now we're going to see if we can get the flags on the same line. That would be really sweet. Okay, and then we have a list of flags somewhere here. Yeah. What am I even doing? Actually, we don't need the F suffix because we know that they're flags. And there we'll do the new line, yeah. Right, so that's our dump. Let's see how this actually looks like. Oh, wait, I forgot to actually implement the setters. That's silly. Okay, I guess we get to do more exciting text editing. What am I even doing? Okay, so there we go. True. Okay. So we tried to run a ret, and that's when we died. Oh, because this binary does not exit. So normally we just ret from main, because like I was saying earlier, like the actual function that you normally start in is _start, which has a call to exit in it. Because let me show you _start in the C library. This is like the real entry point in C or C++. So we like initialize malloc and stuff like that, and I call global constructors, and then we call main, and then we actually exit. So here it goes to syscall to exit from here, from start. So since we're going directly to main now, then we don't get a syscall to exit. So instead we're trying to do a ret, but I guess we should fail sooner in the ret case. Right, so we're trying to execute it before. So this will just be our little hack here. Takes me remove this hack once it's no longer needed. Okay. And maybe we should nicify the output a little bit here. We'll like print out the instructions in yellow instead. And now I forgot to look at the output to see if it was nicely formatted. Wow, it was really not nicely formatted. What on earth? Unhandle final X. Oh shit. Okay, so there's there's a terminal crash. That's stupid. Yeah, we should probably fix that terminal crash, but I'm not going to fix that right now. So I'm just going fix this later at some point. Maybe I'll be a good boy and make a little text file about it. Okay. Close. Yes. Term crash. Okay. So bin true. Clearly it doesn't fit on one line. I was just hoping. Well, we can always resize the terminal. That's why resizing was invented after all. Okay. So now we're actually running this instruction, which zeroes out EAX and sets the 0 flag correctly. Pretty cool. So let's try to, I guess we can also like echo the return code. Yeah, so it returns 0 for bin true, and if we run bin false, it also gives us 0. Wait, is that just a shell bug maybe? No? Oh yeah, right. Because we're not making the exit syscall now. We're breaking out because of this. Okay, so that's fine. Right. But this is really awesome. So what's like something much bigger and scarier? Maybe we can go in like userland and let's see, like count by line and then sort. So simple, yeah, true and false are very simple, and then we have a sync, which I guess is just making a sync syscall, so not very exciting. Clear and TTY. Yeah, so this immediately gets like a lot more complicated because it starts calling printf and things like that. So we'll need like a ton of instructions. I think maybe we're going to be happy here for today and just wrap this up. So I think we made a very interesting start of a very interesting project. So let's pack this up. Let's see. So this was just fixing up the main loop. User space emulator, break out of emulation, and hitting a ret instruction. Until we grow. Until we learn more instructions, we'll have to exit somewhere. So let us exit. I'm cheating. When we hit a ret instruction for now. And then user space emulator, add x86, add arithmetic CPU flags yeah. Implement. Yes. Note that this is a partial implementation since we don't have support for memory variants, memory mod. What do we call it? Mod RM addresses yet. yeah. Variants. But yes, that's very, very cool. Quite interesting. Okay, so I think this will be it for today's video. So I just wanted to get started on this project and start sketch out the sort of the main loop of it all, so that we have a way to approach this work. And I think from this point, it's basically just now it's going to be a matter of fleshing out the soft CPU and implementing more syscalls as we go, and of course refining and making things like a little more general, because there are so many different XOR variants of the XOR instruction. So the way that we implemented this right here, you can see that this is like one particular XOR variant, and we have all these other ones. And there are certainly ways that we can find to share this implementation, because a lot of it will be identical. So a lot of things that we can do, but I think I'll be taking like an incremental approach to this, and definitely going to be drawing on like previous x86 emulation experience. But yeah, this is a good start. So been simple, very, very cool. So I think this is going to be really, really, really useful. It's just going to take a while before it becomes useful, but when it does, we'll have a really, really powerful thing. So yeah, this is it for today's video. So if you made it this far, then I thank you for watching and for hanging out. I hope that you found this stuff interesting. I think this is something I've wanted to have in the system forever, and I always kept thinking like, oh, we'll just maybe port some utility or something eventually, but like as I grow a bit more confident in my own abilities over time, I started feeling like, you know what, why don't we just build this ourselves, right? So I'm glad that we start doing that. Anyway, that's it. So thanks for hanging out, and I'll see you next time. Bye.